Hello, today we'll discuss the principles of amplitude modulation. The topics to be discussed today are elements of communication system, concept of modulation as well as the need for modulation, signals in the modulation process, types of modulation, continuous wave linear modulation, time domain representation of amplitude modulation, and the power calculation of AM wave. Now, before going into the deep discussion of the modulation, we should know about the elements of the communication system. The very important first element for the communication system is to collect the physical data such as the temperature, voice, etc., pressure. So these are the input of the as a physical variable available in the surroundings. Suppose we want to transmit voice. So at the time, voice is the physical parameter. The voice could be defined as the acoustic vibration which is produced by our tongue. So how this voice will be converted into equivalent electrical signal which will be sufficient to transmit over a long distance? So obviously we need a converter that will convert the acoustic vibration into the electrical signal. So such a device is known as microphone. Microphone is a type of transducer. So transducer in common converts the physical parametric variation into electrical equivalent quantity. So that is why input transducer is an important element of the communication system, which is acting as the first stage of this communication system. So this input transducer collects the physical parametric variation and converts them into the equivalent electrical signal. Therefore, the input signal which is going into the transmitter is a circuit which is responsible for transmission of the signal, because whatever is the input transducer produces, that is of low power signal. So power of the signal has to be raised. There are some other requirement of the transmitter we will discuss in the next slide. So all these requirements are fulfilled by transmitter, and the equivalent transmitting signal has been transmitted to the channel. Now what is channel? Channel is nothing but the medium through which the electrical equivalent signal could propagate. Now this channel may be wired, may be wireless, be optical fiber. So there are several types of channel which are available. Now this signal, when that means the transmitted signal, when propagating through the channel, it acquires several types of distortions or errors. So that is why another block is showing that distortion and noise which are also input to the signal in the channel. So these are unwanted. These are produced by several machinery present in the channel, as well as man-made noise, device-made noise. All these things are added to the transmitted signal, and this signal is received to the receiver. Receiver receives the signal and then process the signal to produce the output signal which is suitable for the output transducer. Now this output transducer is again another type of device that produces physical variation. That means the suppose for sound it will be the acoustic vibration which is produced by the output transducer. So therefore output transducer must be a loudspeaker. So therefore electrical signal which is produced by the receiver received by the output transducer and produces the corresponding equivalent physical parametric signal. The concept and need for modulation is an important fact before going deep into the modulation system. Now what is modulation? Modulation is a process by which a low frequency message signal, that means whatever is the physical parametric variation, that has been converted into electrical equivalent signal by means of transducer. So transducer produces the signal which is uh, low frequency as well as low power signal. Now, these signals are not sufficient to transmit over a long distance through the communication medium, such as the coaxial cable, twisted pair line, or wireless communication or optical fiber communication. That means whatever is the low frequency, low power message signal, they needs some carrier who will carry this low frequency, low power message signal to a long distance, and afterward that carrier will be removed so that the message could be extracted for the receiver purpose. So the process of uh, converting this message signal, that means riding this message signal over the carrier signal, is known as the modulation process. Similarly, at the receiving end, when the message is extracted from the modulated signal, it is known as the demodulation process. Now, what are the need for modulation? We need modulation for the reasons such as reduction of antenna size. Now, this is happening due to the modulation because the low frequency message signal is converted into the high frequency carrier signal, that is known as the modulation process. So, carrier signal is a high frequency signal which carries the low frequency message signal. So, therefore, the overall frequency of the modulated signal is shifted to the high frequency domain. So, when the signal is having higher frequency, it will have very low wavelength. That is, the wavelength of the signal has been very low. And we know the antenna dimensions are proportional to the wavelength of the signal. So, as the wavelength of the modulated signal is low, therefore, the dimension of the antenna is also low. So, therefore, reduction of antenna size is possible by modulation. No signal mixing. That means the signals are well separated after modulation in the channel. So there are several modulated signal due to several requirements. Suppose voice is transmitted, pressure is transmitted, temperature is transmitted by modulation process. So these signals should not be mixed. So modulation ensures that the carrier signal, if having different frequency, then the signal will not be mixed in the channel. Increased communication range. The range of communication means 5 kilometer or 7 kilometers. So by distance, if we measure due to the modulation, the communication range is also increasing because the signal are getting higher power, and as well as they are separated with other modulated signals, so they can be transmitted over a long distance. Multiplexing of the signal means the signals which could be accommodated over the channel and they will not be mixed in the channel. At the receiving end, they can be well separated by the process of demultiplexing. Possibility of bandwidth adjustment. It is possible because once we know the carrier frequency and the message frequency, we have a mathematical calculation of the bandwidth, and where it is centering, that is also known. So therefore, if this information is known to the other station, they can produce the bandwidth as well as carrier frequency, which will not be mixing with the first one. So therefore, the bandwidth adjustment as well as monitoring could be easily understood and maintained for this modulation process. The reception quality will be improved because the message signal is not transmitted alone. It is riding over the carrier, which is known as the modulation process. So therefore, carrier takes the responsibility of the message to bring it into the long distance, and at the receiving end, they will extract this message, and therefore, it will ensure the quality improvement of the received signal. The signals involved in the modulation process, that means we utter about the signal in the modulation process. First are the message signal and carrier signal. Message signal means the information which are of low frequency, low power, but the carrier signal is of high frequency and high power. This is obvious because carrier has the responsibility to bring the message over a long distance by means of modulation process. That is why carrier frequency is high as well as carrier signal power must be high. The modulated signal is the resultant signal which is produced due to the modulation. That means when the message is riding over the carrier signal, the resulting signal is known as the modulated signal. So this modulated signal is a combination of the modulating signal and the carrier signal. Now there are various types of modulation. That means the classification of modulation is also another important sector. Normally, any signal is having the magnitude, the frequency, as well as phase information. So when a message signal which is showing the variation in the information in terms of magnitude with respect to time. So if this message magnitude is varying the carrier amplitude, then we are telling it is the amplitude modulation, because carrier is also a electrical signal that is also having the amplitude, phase, frequency, all these three parameters. But we should remember that message has the information residing only in the magnitude, not in the phase, not in the frequency. So that is why message signal has to be introduced into the carrier. Now, in which part of the carrier the message will be introduced? It may be amplitude, it may be frequency, it may be phase. So that is why if the message signal is introduced into the carrier amplitude, that means if the carrier amplitude is varied according to the variation of the message amplitude with respect to time, then the resulting modulation system is known as amplitude modulation. Similarly, there is angle modulation in which two parameters are dominating, one is frequency, another is phase. So if carrier frequency is varied according to the instantaneous magnitude of the message signal, then the resulting modulation is known as the frequency modulation. Again, the carrier phase, if varied according to the instantaneous magnitude of the message signal, then the resulting modulated signal is known as phase modulation. There are some other kind of modulation which is known as the pulse modulation. In the pulse modulation, the carrier is a sequence of pulses. That means the pulses are placed at equal distance of time of unity magnitude. So if this unity magnitude equidistance pulses are multiplied with the message which is analog in nature, we are getting discrete time continuous magnitude signal. So that is also, as the magnitude is constant continuous, therefore it is also analog modulation. And in this analog modulation, pulse amplitude is varied with respect to time. That is why it is known as pulse amplitude modulation. Sometimes the width of the pulse is varied according to the instantaneous magnitude of the message. Then this is known as pulse duration or pulse width modulation. There are another kind of modulation which is also analog in nature, known as pulse position modulation. That means the position of the pulses initially equidistant from other pulses, but when the modulation is occurred, the position of pulse is changed or varied according to the instantaneous magnitude of the message signal. So this position of the pulse may refer or may center with respect to its leading edge or with respect to its trailing edge. So these are analog modulation. There is also digital modulation in which the magnitude is constant. That means magnitude is not continuous, but it is a fixed magnitude for the digital modulation, in which the carrier signal may be pulse, but the carrier magnitude will not be continuously varying, but it will produce discrete magnitude with respect to time. So such a modulation may be pulse code modulation, where each of the pulse magnitude is further converted into binary codes. There is a delta modulation in which comparison of the successive pulses are compared. Now let us move into the continuous wave linear modulation. In the continuous wave linear modulation, that means it is nothing but the amplitude modulation, in which the amplitude of the carrier signal varies in accordance with the instantaneous magnitude of the modulating signal. So this means the amplitude of the carrier signal containing no information varies as per the amplitude of the signal containing information. That means the message signal. Now this is the overall diagram for the modulated signal, amplitude modulated signal. On the left hand side, it is showing the baseband signal or the message signal, also known as information bearing signal. It is having the maximum magnitude capital F suffix M. So this is again, there is a negative magnitude. So positive magnitude, negative magnitude, both are shown. So it is a normal sinusoidal signal, a cosine wave. On the in the middle, it is showing the similar cosine wave, but the frequency is larger compared to the message signal. The amplitude is capital A suffix C. This is known as the carrier signal. The resultant modulated signal on the right hand side, it is showing that the same carrier signal is present in the modulated signal, whereas the instantaneous magnitude of the carrier signal is varied according to the magnitude of the message signal. So somehow the message, which is the low frequency signal, has been superimposed on the carrier signal. That is why the envelope or the upper layer of the carrier magnitude is varied according to the instantaneous magnitude of the message signal. So this type of modulation is known as amplitude modulation, which is having maximum amplitude as well as minimum amplitude as indicated at the top. So these are responsible to find out the depth of the modulation. We will discuss in the next slide. Now the time domain representation of amplitude modulation uh, is an important calculation which is uh, discussed here. First, we have to consider the message signal. Let us have a mathematical expression mt is equal to am cos of 2 pi fmt, in which fm is the message frequency and am is the message magnitude. The carrier signal shown is carrier, that is also another cosine wave, where fc is the carrier frequency, and we should remember that carrier frequency is much larger compared to the message frequency. Now here it is showing that St is the resultant amplitude modulated signal. Now how this equation has come? It is coming that the modulated in magnitude, that means instantaneous magnitude of the modulated signal, less the carrier magnitude, that means AC, is proportional to the instantaneous magnitude of the message, that means MT. So if we solve this equation, we will get finally ST is equal to AC plus AM into cos 2 pi FMT within bracket multiplied by cos 2 pi FCT. Modulation index is an important parameter for amplitude modulation as well as any modulation process. Now this modulation index finds the depth of the modulation which is required to find the modulation in terms of percentage. So once we got the final equation for the modulated signal, it could be further manipulated to write in this fashion. St is equal to, if we take AC common, then it will be 1 plus Am by AC into cos 2 pi FMT. So this ratio Am by AC is nothing but the ratio of the message magnitude to the carrier magnitude, obviously maximum value. So this ratio is known as the modulation index, and the percentage of this value tells the percentage of modulation or depth of modulation. Now this depth of modulation is having the limit. It should not be less than 0. It should not be higher than 1. So within 0 and 1, the value of this modulation index varies. If we further continue the modulation index, we are getting A max, that means the maximum magnitude in the modulated signal is AC plus AM, and the minimum magnitude of the modulated signal is AC minus AM. So if we use these two maximum and minimum magnitude from CRO, we can calculate the depth of modulation. That means if we take the difference and if we take the addition of these two maximum and minimum value, we are getting two things, twice AM and twice AC. If we take further the ratio, the difference magnitude by the summation magnitude, then we can get the same expression, message magnitude by carrier magnitude. So that is also showing the depth of modulation, but this calculation is possible from CRO, because in CRO we are visualizing the time domain uh, representation of the modulated signal. So that is why we can easily calculate the depth of modulation from CRO using this equation. The bandwidth of amplitude modulated signal is another important parameter, because once we know the bandwidth of the amplitude modulated signal, we can avoid the interference of such a amplitude modulated signal with other amplitude modulated signal. We know the carrier frequency is higher than the message frequency, so carrier frequency is centering at certain point, and bandwidth is encompassing the carrier frequency with certain range of frequency. So for that range of frequency, information lies on the frequency domain, so it should not be interfered with other modulated signal to uh, protect the information in the modulated signal. So bandwidth can be easily find out from the final expression of the modulated signal, in which we already have seen uh, that there are two sidebands. So how to find out those two sidebands? First, we have written the expression of the amplitude modulated signal is equal to AC into 1 plus mu cos 2 pi FMT within bracket multiplied by cos 2 pi FCT. If we enter the cos 2 pi FCT into the equation, then we are getting the carrier signal as well as two sideband signals, upper sideband and lower sideband. So this upper sideband and lower sideband are the two edges of the amplitude modulated signal. So if we take the difference of these two edge frequency, Fc plus Fm and Fc minus Fm, then we can get the overall bandwidth for the amplitude modulated signal. So this is nothing but twice the frequency of the modulating signal. So we should remember, once we are increasing the frequency of the message signal, the corresponding bandwidth of the amplitude modulated signal is also increasing. Thereafter comes the power calculation of AM wave. So this is one of the important calculation for the amplitude modulation. So again, if we write the overall equation with the carrier signal, so first equation is written, which is very much important. It is showing three parts of the modulated signal. One is the unmodulated carrier. AC cos 2 pi FCT is the unmodulated carrier signal. So the important fact is that the carrier signal, which is unmodulated, is also present in the modulated signal as one part of the modulated signal. So this part is not required in the modulated signal because it does not carry any information. So unmodulated carrier signal in the modulated signal equation is unwanted. So that is one of the disadvantage of amplitude modulation with carrier. Thereafter, upper sidebands and lower sidebands are shown. So if we want to calculate the total power, so it is the summation of the carrier power, upper sideband power and lower sideband power. To find out the power of the cosine signal, we need to find out the RMS power, because it is a AC signal. That is why AC signal power is normally calculated in terms of the RMS value. So that is why V RMS square by R has been taken, where R is the load resistance. And if we take R is equal to 1 ohm, then we can easily calculate the power of the signal. The power calculation of AM wave is having three number of parts. One is the carrier power, another is the upper sideband power, and finally lower sideband power. So if we add all these three, we are getting the total power in the amplitude modulated signal, which is the carrier power multiplied by 1 plus mu square by 2. Now, in this total power expression, it is very much clear that carrier power is consuming most of the power from the total power of the amplitude modulated signal, and this is nothing but a disadvantage which is present in the amplitude modulated signal because it does not carry any information. So if we consider mu, that means modulation index is equal to 1, then we are getting the maximum power possible from the amplitude modulated signal, because modulation index is having the highest value 1. And if the modulation index mu is equal to 0, that means no modulation. At that time, Pt is equal to Pc. That means unmodulated carrier power will be the total power of the modulated signal once mu equal to 0. So no modulation means the carrier power, and full modulation means 3 by 2 times of carrier power. Thank you.